Stancu from Concordia, who's going to tell us about the fundamental gap of convex domains in hyperbolic space. Please.
Thank you very much for the introduction, and thanks to organizers for the invitation to the Institute and for the opportunity to talk today. Before I start, I should say first that this is work with a number of collaborators over a series of papers, and so I should list them: Theodora Burni, Julie Clutterbach, Hein Nguyen, Guofang Wei, and Valentina Wheeler. And this is on a somewhat classical problem. So I'm looking first at the eigenvalue problem of the Laplacian, and maybe occasionally I'll mention the Schrodinger operator as well, but mostly will be that V is 0 with Dirichlet boundary conditions. And we know that the spectrum of this problem is discrete, diverging to infinity. And moreover, we know that the first eigenvalue is strictly positive and simple. Therefore, there is a difference between the lambda 2 and the lambda 1. And this is precisely what is called the fundamental gap of a domain. And this is the main object of the talk. This is also true, the spectrum being discrete and the gap being, well, the first eigenvalue being positive and having a simple is also true for any domain in any Riemannian manifold where we take the Laplace-Beltrami operator. In this talk, things will be relatively simple. We have as manifold Rn, Sn, and mostly the hyperbolic space. So to say a few words about the gap, it's been the object of two conjectures, actually. So the first one in 56, Payne, Polya, Weinberger conjecture, said that for any domain on a simply connected space of constant sectional curvature, then the fundamental gap is bounded above by the fundamental gap of a ball, normalized so the ball has to be such that the lambda 1 of the ball is the same as the lambda 1 of the domain, and this normalization is needed, obviously, or some normalization is needed. And you might have seen this conjecture in a different format as a ratio of lambda 2 over lambda 1 being maximized for the ball, but for the reasons that I'll be using it in this form later, I'll state it as such. And this conjecture, although we still call it PPY conjecture, has been proved successively in the Euclidean and then in on the sphere, and for convexity reasons in the upper hemisphere, and or in one hemisphere. And then the last case solved by Ben-Gurion in 2007 was for the hyperbolic space. So this is an instance where the fundamental gap behaves absolutely the same in all spaces of constant sectional curvature. And this is primarily one of the reasons I brought it up. But there is also a secondary reason. So I want to give just one hint of the idea of the proof, because it will be also used in my talk as well. So the eigenvalues have a variational formulation. Everybody knows using the Rayleigh quotient, and we take minimizers of the Rayleigh quotient over different spaces. As we progress with lambda n, we look for the minimizer over subspaces that are orthogonal or complementary to the ones that were spanning the previous spanned by the previous eigenfunctions. So particularly if I have lambda 1, the minimizer of all functions that are 0 on the boundary and in W12, then for lambda 2, I will take functions that are orthogonal to lambda 1, to V1, to the first eigenfunction, and orthogonalities with respect to del 2. So here the integral over omega of W and V1 should be 0. And so the point here being that if you want to find an upper bound, actually you have an easier life than finding a lower bound, because lambda 1 has some chance of being calculated or get a good estimate for, and then if you want to estimate the difference lambda 2 to lambda minus lambda 1, it suffices to take a good test function for lambda 2. And so a good test function involves finding, so for example, this is the approach that was used in the PPW conjecture. You take a function P, a smooth function P, such that the test function will be PV1, and you choose P such that PV1 squared is 0 because you want the orthogonality condition. And then there is some symmetrization as well involved. This P is here the one of the Weinberger coordinate functions, and then some symmetrization is involved, and this helps in finding that the upper bound is realized for spheres, for balls. Okay, and so the idea is that you don't really need to calculate lambda 2. If you can find a good test function, you might be able to prove an upper bound. And for the lower bound, let me start with something completely trivial. We look, so this is immediately a first case where the potential disappeared. So I take the interval and I look at so-called spectral problem on the interval, and we very quickly see that the difference between the first two eigenvalues is 3 pi squared over L squared. And then we do the same for a rectangle. Let's choose for simplicity that capital L is greater than little l. So capital L is the length and little l is the width. And again, with very simple analysis, so these are very few cases where we actually can calculate the gap. And the gap is 3 pi squared over L squared, exactly, this one. And it's greater, strictly greater than 3 pi squared over d squared, where here d, let's say, is the diagonal. Is in fact if you want, is the diameter of the set, in the sense that is the maximum of the distance between any 2 points. And this is true for any width. And of course, if we let the width go to 0, we recover the first case, the interval case. So we actually do reach the bound 3 pi squared over, we reach the 3 pi squared over d squared, right? Because then in that case, the diagonal becomes exactly the length of the rectangle. And so this is done because I wanted to bring up the question of the lower bound on the fundamental gap, which was also a conjecture raised separately by Vandenberg in physics in 83, and then Yao and Ashbaum Manguria later, coming from different areas, sort of geometric analysis, more spectral theory. And it is not accidental that Vandenberg is asking this, because the gap has some significance in physics. So you probably know better than I do, is it measures the energy needed for a particle to go from the ground state to the next level state of energy. And so the fundamental gap says that, or asks, or claims that for a bounded convex domain, the Schrödinger operator, not necessarily only the Laplacian, with a positive and convex potential, has a lower bound, has a lower bound on the fundamental gap, which is 3 pi squared over d squared, which is exactly the thing we saw before. And in fact, the conjecture continues saying that this lower bound is approached when the potential is constant, not necessarily 0, because you can incorporate the constant into the eigenfunction, but let's say 0, and then the domain is degenerated to this needle-like rectangular box. And this happens in higher dimensions as well, not only in R2, but in any Rn. And notice that for the upper bound, we did not need the convexity. For the upper bound, compactness was enough, or boundness of the domain. Here we do need convexity, and it's relatively simple to see that if you have a disconnected domain, actually I'm going to bring this up. If you have a dumbbell-shaped domain, which is not even disconnected, you can find that the fundamental gap is relatively small, can be made arbitrarily small can be arbitrarily close to 0. And okay, so so the conjecture was made in 83 first time, and then for a while the progress was relatively slow. There were some partial results, some lower bounds, first by Singer, Wang, Yao, and Yao, pi squared over 4d squared. So remember the conjecture bound is 3 pi squared over d squared. And then was later improved by a couple of people. In fact, there are more results improving this to pi squared over d squared, and I'm going to come back to this. Different methods, but both methods, particularly the pi squared over d squared, is due to the low concavity of the first eigenfunction of the operator. And so Zinger, Wang, Yao, and Yao, they used a gradient method, so they compare the maximum and the minimum of the gradient, norm of the gradient at the points on the domain. This pi squared over d squared is really capitalizing on the low concavity in a different way, is using a comparison with a one-dimensional model, and I'm going to bring this up a bit later again. And then there is the complete resolution of the one-dimensional case, which only came in '94. Maybe in between, I should mention that in '89 there was a one-dimensional proof by Ashbao and Ben-Guria when the potential is symmetric. So on an interval, and it's symmetric or convex, and it's symmetric with respect to the middle of with respect to the endpoints of the interval. And then, okay, so then we had further improvements. The next one, I think, was 3 pi squared over 2d squared. And eventually, the fundamental gap conjecture was solved in 2011. And again, I will say a little bit about these modulus of continuity and concavity, because this is basically a stronger way to quantify how log concave the first eigenfunction is. And so this was really the thing that was needed in proving this lower bound on Rn. Once the fundamental gap was settled on Rn, people started looking at this on the sphere, for domains on the sphere, and they were putting together all the papers that were on this. So eventually was solved with the same lower bound and with the same degenerating case. This is not, however, for a potential. This is just for the Laplacian. And so because both the Rn and the Sn displayed the same behavior for the lower bound of the fundamental gap of the Laplacian with the Dirichlet boundary condition, it was natural to ask what happens for Hn, since for the upper bound it all holds the same for all three spaces of constant sectional curvature. So let's look a little bit at what was common in the case of the Euclidean space and the ball. So like I mentioned before, the low concavity played an important role, and it's actually sufficient to prove the bound in the Euclidean and the spherical case, to prove the bound pi squared over d squared by comparison along geodesics, or along straight line in Rn, with a one-dimensional model, which is the model given by the equation 1, which is a simple second-order linear ODE. And with some particular coefficient to u prime, which is given for the sphere here and for the 0 for the Euclidean case. Okay, you could not do better than this on a better bound using just this comparison, because this comparison is along geodesic, so it's one-dimensional. And it kind of loses control over what happens transversally from the geodesic. And as you move away, you move toward the boundary of the domain, the transversal intersections become smaller. So there should be less mass in that area as you go closer to the boundary. Okay, so that was not captured. And that's why when I was mentioning that Clutterbuck and Andrews had a different approach, they actually found a 2-point modulus of concavity that measures the concavity of the eigenfunction in a stronger way, that takes into account value of the eigenfunction and the gradient of the eigenfunction at first eigenfunction at 2 different points on the domain. And they look at this, and they were showing that this is basically, well, they were using a heat equation, and they were showing that always improving. This modulus of concavity is always improving. It's a little bit more technical to say, but the point is that, there was a common denominator to the proofs in Euclidean and on the sphere. And so what happened in the case of negative curvature is that you can still look at the one-dimensional model, and you can see that the comparison with the one-dimensional model tells you the first eigenfunction of the domain omega is more log concave than the eigenfunction of the one-dimensional model. The one-dimensional model that you should heuristically set up for the hyperbolic still exists, and the function, the one-dimensional function, the function of the one-dimensional model is still log concave. Okay, but there is, even if your function will be the first eigenfunction on the domain of the hyperbolic space will be log concave, the concavity will still, the comparison will still fail, because in the comparison you're using the fact that the space has positive curvature, and since it is a comparison, you're kind of using a certain inequality, and the terms concur to give you the right direction of the inequality. So the positivity of the curvature is important. So even if you would try, even if you know that for all eigenfunctions of domains in the hyperbolic, you have that the function is log concave, this will still not be enough to prove the bound pi square over d squared, but this will still be something that could be useful. Okay, however, in 1989, she gave a counterexample showing that the first Dirichlet eigenfunction of the Laplacian on some convex domain on the hyperbolic is not log concave. It's not even quasi concave. In fact, the proof goes through the fact that takes a certain domain in the hyperbolic, which I'll bring up shortly, and shows that the level, that if you play a little bit with the parameters defining the domain, one of the level sets of the eigenfunctions will fail to be convex. And so this proves that it's not quasi-convex and therefore cannot be log concave. So the starting point for our work was basically studying this paper, understanding exactly what is the characteristic of that domain. And in the process we showed, but not for that domain, we showed that in fact there are domains in the hyperbolic plane that violate the conjecture bound. So there is at least one domain in H2 such that the fundamental gap is smaller than 3 pi squared over d squared, where d is the diameter. Okay, so so as we see further, we got stronger results, but that was the starting point. And actually there is some heuristic here that can be taken further, and in fact it was taken further to prove other results. So I thought it's worth spending a few minutes on this. So in Shish's example, we take the Poincaré half plane. We take this model and we choose to change to polar coordinates. Okay, the polar coordinates are not geodesic coordinates, at least not the theta constant is not a geodesic. But it allows you to use, to form some rectangular domains and therefore use separation of variables, because it's very little, like very tangible calculations you can do for the eigenvalues unless you choose either some rotational symmetry or some separation of variables. So here is the family of domains that Shish took. So he considered this quadrilateral RQSP, where, okay, so there are certain parameters. So the C can vary, can go higher or lower, and the theta, the opening of the domain theta 0, theta 1. It turns out that the non-symmetry of the domain was not important, but that is the domain he started with. And for some values of C, theta 0 and theta 1. So it was basically an intermediate value theorem studying the curvature of the eigenvalue, the level sets of the eigenfunction. And for some values, it proved that the domain is not convex, and therefore the function is not log concave. And these are the exact values. So it was not really, it's a pretty computational part. However, we show that for this domain, even if the first eigenfunction is not log concave, we show that we get a bound which is better than what we usually got in Euclidean on spherical if we had just the log concavity. The bound that we get directly there was pi squared over d squared, and this is 3 pi squared over 2d squared. So it seems like the log concavity was not necessarily playing a role. And then, in fact, we showed further that, I mean, we kind of looked a little bit closer, and you can ignore most of the things here, but maybe the idea here is that if we look at this quantity, which if it would be greater than 1 will be the lower bound of the conjectural lower bound, we were able to show that for domain of that sort, you can have some squeezing between two quantities depending on some parameters of the domain. And therefore, we were able to find that you can have some theta, some opening and some C such that this will be less than 1. And therefore, we have that fundamental gap is smaller than 3 pi squared over d squared. So this was the idea of the proof. And as we did this, we realized that, in fact, we can do a lot better. It was a little bit later. In any dimension and for any epsilon and any diameter, or maybe I should start for any diameter and any dimension, or for any dimension, any diameter, you can find a convex, and then you fix an epsilon, you can find the domain that has the diameter, and the lower bound is, the fundamental gap is sufficiently close to 0. So it's basically it's the lower bound will be 0. Okay. So how did we do this? So basically, this is a Schicht domain, but with a much, rather with a thin kind of, I don't want to say, like the inner radius is very small. So here in the middle, UT has a much smaller distance than PQ and RS because we are in hyperbolic, and and then the domain is symmetric. It doesn't, so it opens up on both sides with the same angle. We wanted to, so maybe I should say, so what I wanted, in fact, to point out is that here what we're going to do is kind of say that the diameter is reached on a kind of a diagonal RP or SQ, right? And if we make these domains thinner and thinner, so if in fact we get this width to go to 0, we kind of replicate the needle-like in the Euclidean case. But in this case, and we reach the lower bound, but in this case, the lower bound is actually 0. Okay, so heuristically, this is what it is. And the actual work is to say, all right, so let's do the separation of variables. This mu bar will turns out to be mu or 4 mu and so on and so forth. And the eigenvalues, the first eigenvalue of the domain, the blue domain, is in fact the first eigenvalue of this problem with mu here. And the second eigenvalue is not that. It's a minimum between two things, but it's the fundamental gap of the blue domain is smaller or equal than the fundamental gap of this one-dimensional problem. So basically, we just have to understand what's going on with that problem. And okay, so before I go into actually showing why this the fundamental gap is actually arbitrarily close to 0 for a specific width, let me just say also again heuristically the fact that this domain has a very thin middle. It makes it that, and this is more visible when we move to the Poincaré-Diss model. This makes it so that the domain is it resembles more the dumb shell figure in Rn or in R2 than a convex domain in R2. So what happens with the fundamental gap of this domain? Well, you can think heuristically that you have U1 function, the first eigenfunction of this disk over this disk, and the first eigenfunction over this disk also oriented the same way up here. And then they're connected by some smooth function on the neck. And then for the second eigenfunction, you can think that you reverse the first eigenfunction on this one, and you still connect somewhat smoothly on the neck. And so the two functions are orthogonal to each other. And when you look at the Rayleigh quotients, basically you can make them sufficiently close to each other if the neck is sufficiently narrow. And this is why also this fundamental gap will not hold for a non-convex domain in Rn. Okay, so the domain that we took resembles more this. And in other words, the eigenfunction, the first eigenfunction, is in fact a positive function on the domain, but it has a two peaks form, two inflection points here.
Can you send the gap to 0 for any diameter? You need to have a large diameter.
No, it's for any diameter. So
it could be very small.
It could be very small, yes, because what happens is you're playing with the width, in fact. The diameter can be small, but then you take the two geodesics that are here to be closer and closer together. And this is, in fact, where that will make the difference. So actually, this will come up here. So as I mentioned before, the fundamental gap of the domain will be given by, will be upper bounded by the fundamental gap of that one-dimensional problem. For the one-dimensional problem, we can write explicitly the Rayleigh quotient. And we can actually see, we made a kind of a delicate analysis of this eigenfunction. When the domain becomes smaller and smaller, these peaks go closer and closer to the end, and this becomes flatter. And this will actually play a role because it means that the gradient of the function is very small on some on some interval that we can bound from below. And so for the second eigenfunction, we're going to take for the second eigenvalue, we're going to take a good test function, which is very similar with the PV1 that I discussed in the PPW conjecture. So I'm going to take a odd function that I multiply, so phi or xi, that I multiply my first eigenfunction that here I call phi1. So maybe I should have kept p and v1. And so this is the equivalent of the Weinberger trick, and we have that. So this is the blue one is the graph of the first eigenfunction of the problem. The dotted one is the graph of the test function that's sufficiently close, and so by controlling very well what's going on here, because we know that this is almost flat, we can actually make it so that this difference of the Rayleigh quotient is very small. All right, so that was the conclusion of the fact that there is basically no fundamental gap as such for the hyperbolic space. But then one can question the definition of convexity, or can ask for a stronger notion of convexity. So the convexity that we use so far, or usually we use on manifolds, is the geodesic convexity, that any domain has, for any domain, any 2 points can be joined by a geodesic segment that's in the domain. In Rn there is an equivalent definition which says that a set is convex if for any point on its boundary the support hyperplane, so the set lies always in one side of the support hyperplane. So more generally you can say that omega is the intersection of all its support hyperplanes of the boundary. Okay, we don't have this generally on Riemannian manifolds, but we do have something very similar in the hyperbolic, which is due to Santa-Law, or at least one of the early references is due to Santa-Law, that you can have a convex, so you replace the support hyperplane by support horosphere or horocycle. Maybe this is easier to see on the hyperbolic disk model. So if this is the hyperbolic disk, the horosphere or horocycle in this case will be any sphere that has the center at infinity, right? So the spheres are on on the hyperbolic space. They look like Euclidean spheres, but their center is off, it's closer to the boundary. And so when it gets exactly here, it means that it's a horosphere, so this point is not included, and so on. So it's really the perfect equivalent of having a hyperplane, right? Because the center is at infinity. And so the question is whether there is, or the question was whether there is a fundamental gap that holds for horoconvex domains, because this is a stronger notion of convexity. You can't have this narrow waist if you have horoconvex sets.
The principal coefficients
Exactly.
by one. Right?
Here, yes. I put it on the second one. Yeah, so basically, exactly. So convexity in general it means that the Hessian, the second fundamental form is positive definite, but so zero. But if you actually ask for a horoconvexity, it means that the principal curvatures of your surface have a curvature greater or equal 1, and this is actually given by the sectional curvature being -1. Otherwise, you'll have to scale it accordingly. All right, so therefore horoconvexity is a stronger notion. So you can imagine a horoconvex set will be intersection of such spheres, such horospheres in the 2 dimensions horocycle. So it's really fat. It's like a ball kind of body. In convex geometry now there is a whole study of ball bodies which are intersection of balls of a certain radius, and therefore there is a lower bound on the curvature. Okay, so disregard this theorem. Look only at the first one for the moment. This is what I call the third main result. This says that for every dimension of the hyperbolic space, there exists a constant depending on dimension, such that if the diameter is larger than 4 ln 2, and this actually can be lowered, but you will see it doesn't quite matter that much. It's true that this kind of says that for diameter that's large enough, you will have that the fundamental gap goes to 0. So this answers your question. Is different than in the usual convexity, where you have for every diameter that the fundamental gap is close to 0, could get close to 0, but this is only for relatively large diameter, but given that the diameter lies between 0 and infinity, this is a pretty good bound. So we proved that the fundamental gap is bounded above by the constant over d cubed. So if we move d squared to the other side and we push d to the infinity, obviously this will show that the fundamental gap as stated, the fundamental gap conjecture as stated cannot hold even if you restrict to another class of convex sets. This looks like it's a corollary or a weaker thing, but in fact this is how we proved the upper theorem. So we first proved this for balls, right? So we first proved this for balls, and then using this I can show how, in a very simple way, how the other one holds. For balls, basically it was a careful analysis of the asymptotic of the eigenvalues in terms of radius, and we did a slight improvement on the r cube of lambda 1 on the upper bound. So also by a comparison result, or the comparison, so all right, so but that was the hard part. And the first, yeah.
So the power 3 here is not sharp, you're saying, right?
We're not sure. So yeah, so we were, so I will add something about this a bit later, but initially we wanted to show that there is a d cube on both sides, like another constant for the, when we couldn't show it even for spheres. So it might be that it's not a d cube. It must be. What I want to say is that maybe there is another function that could be used to replace the usual bound.
Yeah, because here we don't have a scaling, so it's
exactly right. But let me I get back to that, because there is a recent paper on saying that exists a function depending on n and d that gives a lower bound, but it's not explicit. So keep in mind the second result, that for balls you know that the fundamental gap is upper bounded by a constant divided by 2r to the cube, which is the diameter to the cube. And let's try to prove that this is true for any horoconvex domain.
Can I ask What happens for small diameter?
So we're not sure. We're not sure. It should be that in some sense it's like the Euclidean for very small, right? But we could not prove anything precisely, rigorously. So, all right. So let's take a horoconvex domain or some of some fixed diameter. And choose, so this is, okay, so most of my talk, although I was saying results in Rn, I showed for R2, for Hn I showed for H2, but the proof really carries the same way. But here I start with the domain in Hn. I choose a diameter and I choose the ball of radius R, I call it R omega, that has the same eigenvalue as my domain. Okay, that's clear, it can be done. And then we use the result, actually we ended up reproving it, not knowing that it exists. There is a result by Borisenko and Miguel from 1999 that basically says that for horoconvex sets, the in radius and the out radius of the domain cannot be too far apart. And in fact, there is this constant no matter at what size, about what size balls or what size domains you're talking about. And so in some sense, actually what this said for us already was that if the domains are very, very large, so both R and little r are close to infinity, so the domain should behave more like balls, which is why we search for this C of n over d squared, the d cubed as well, because if it is true for balls, it must be true also for very large domains. So we have this strong fact that horoconvex domains are characterized by this nice relation between the outer radius and the inner radius. And let's take the ball of radius little r. Yeah, so big R, big R is the outer radius, so it's obviously the diameter over 2. So the little r, if you take the inner radius, should be greater than d over 2 minus ln2 from Borisenko's result. And then by the monotonicity of the first eigenvalue, we know that the radius of the ball that has the same first eigenvalue has to be greater than little r, so it has to be greater than this d over 2 minus ln2. And this is where we're using this hypothesis, which is why I said it could probably be, I mean, it can be improved, but it still will not give the result for all diameters. That if we have this, we have that the radius of the ball with the same eigenvalue, first eigenvalue as the domain is lower bounded by d over 4. But then we can use Ben-Gurion's result, which I stated in the beginning, that the fundamental gap is maximized by the balls with the same first eigenvalue as the domain. And since we know the second theorem for balls, so this is less or equal than a constant over 2r cubed, then we have the result for omega as well, smaller than a constant divided by d cubed. So this concludes the proof of the third result. So obviously, so maybe the thing to take home is that the fundamental gap conjecture cannot hold with the same function that it holds for the Euclidean and the spherical space. And so I end with a few results that are not mine, but they are recent and shows that, in fact, probably something else, some other things can be said. And these are all not, I mean, there is one other maybe that I will state orally. So first is that this idea that we had for the hyperbolic, that for convex domains, the fundamental gap vanishes. You can make it arbitrarily small. This was carried also by Nguyen and Khan in any manifold that has a negatively pinched curvature. And in fact, they have a slightly stronger result, but it was a bit more complicated to state. but the paper is on the archive, and I think maybe it's already accepted. There is a second paper that just appeared in Journal of Geometric Analysis that showed that there exists a function depending on the dimension and the diameter such that the fundamental gap is greater or equal than this function, but we don't know much about it. The methods are using Clutterbuck, Anderson-Clutterbuck 2-point modulus of concavity, and they're using a Brownian motion on the 2 points. So the result, the existence of f is obtained by, it's an existence theorem, but not a constructive theorem. Yes.
Is there some simulation for some fixed d to see what the?
No, they're not yet. Yeah. That will be interesting. But they were saying, they were saying that for small diameter, this f it should be close to 3 pi squared over d squared. So I don't know. They should have done some numerics, but not simulations, but some kind. Because this is again obtained with some kind of one-dimensional model, and it's a lot of comparison and so on, and so maybe some things can be improved. And then finally, maybe let's go back to the potential, because in the Euclidean, the result about the fundamental gap actually holds for the Schrodinger operator, not necessarily, not only the Laplace operator. For the sphere is just a Laplace. And here in the hyperbolic, Clutterbuck, Jacqueline, and Nguyen proved that, in fact, the constant potential is actually not optimal. And they're using the same kind of domain that we like, the Shish domain. So it's basically the domain where you can actually do some calculations, and turns out to be the source of a lot of negative answers. And yeah, so lastly, there is one paper that I only saw recently that said that the eigenfunction of the ball is low concave in the hyperbolic, which turns out not to be so easy to prove, which was surprising. So we don't know yet if for all horoconvex domains the eigenfunction will be also low concave, but maybe that's also that. Again, it will not help to use the same derivation as we did as we have in the Euclidean and spherical, but probably it can be helpful. So I'll end here.
Thank you very much. Are there any further questions?
Are there geometric improvement, like in the classical case? If you are close to the fundamental gap, you need to be close to
in the Euclidean, I think I saw something. I think it might be even Antoine. No, maybe not Antoine Arnaud, but Antoine Arnaud told me about maybe Bukur, and yeah, they actually do something, yes, which is very interesting. And I was trying to look at it with a student, but I don't know if it carries over for the spherical, for example, yeah, or something like, or some other of the methods. Yeah, some stability. You're saying, right? Yeah.
The result about the pinch negatively curved manifold, so it's the universal cover of those manifolds, domain in the universal, or it's on the manifold?
On the manifold, yeah. Which is why, yeah, it's needed to be pinched, because I think, yeah, I don't remember exactly the proof, but I can tell you the reference. But they really need it to be strictly smaller than a negative constant.
Consider simply connected pinch negatively curved spaces, then your result also
yes.
is up to quasi-isometry or something.
Exactly. This was brought up, yeah, a few times before. Indeed, it's probably we should have thought about, yeah, writing it, but
there was not in the 1D case. There was not in the non-convex case, the standard. There was not a lower bound by Harel, Simon, or something like that?
I don't know. The conjecture is for a convex and positive V, so I don't know. I didn't check, but it's passive.
So never lower bound. in this case.
Yeah, is it still away from zero? Probably. Yeah, but okay. Yeah.
It's a differential.
Yeah.
And the other point is when you describe your method, I don't remember for the double neck. For the double neck problem, do we have, as epsilon tends to zero, the exact measure of the splitting?
Oh, you mean like the asymptotics of?
I know better the double problem.
Yeah, I don't know. Alexandre might know.
It's small, very small, but is there a main term? That's my question.
I don't know. Yeah, I don't know. Maybe.
Because so for the double well problem in the semi-classical context, one has a main term, and in the way it's proven, at least in the paper I have with Justin, the techniques was more to go a little further. In your picture, you say, I take the left eigenfunction, and then I try to, for the double well problem, the idea was the first idea would be I split in the middle, and I look at the left and right. But at the level of the technique, it appears that one has interest to go further and to use as left eigenfunction, the function where you go further.
I see.
And so
That's why you were asking about the neck. I see.
I think that in your case also, it could be better to look to one problem where you go a little further and see.
Take the reflection. I see.
In our at least in the case of the double well, the double well problem, we get much more. We lose. Because the error term was the same order of what you measure in the middle, so it was important to.
Yeah, I will take a look. Yeah, we didn't think of it. Definitely, it's something to, yeah, maybe to get a finer analysis of that part. Yeah. Yeah, we definitely split straight in the middle and try to do something very symmetric.
Okay, no questions, so let's thank the speaker again.